So this is the end of the section on integral representations. And as I've advertised several times, I really want to kind of take the opportunity to show you one of the really neat applications of mathematical physics, and that's solving the hybrid math. So we're going to approach it as applied mathematicians. And the physics of the hybrid math is not role, we're going to be interested in solving a set of differential problems. And you see where the concept of hypergeometric function appears. And in particular, I want to start off, just because I'm going to need it in the hydrogeometric problem, with a series expansion, with deriving a series expansion for 1f1 from the hypergeometric function. And then we'll finish off with an integral representation for the concept of hypergeometric function, just to wrap things off. But if I don't have time for it, I'm going to give it as an exercise and show how to do it. It's not too difficult. And then in the next big section, I'm going to talk about Green's function. So Wednesday's lecture, the effective Wednesday's lecture, is going to be focused on some revision of Green's function, which I hope you will already be familiar with, but if not, certainly not in the way that I'm proposing we think about it. The Wednesday lecture will bring you up to speed. And then we want to really give a more abstract notion of the Green's function and how it relates to something called the resolved operator. So we're going to give, as usual, an operator analysis of this. So let me quickly just start off by telling you what the series representation for the hypergeometric function is. And to do that, just recall that we had a series representation of the confident hypergeometric function, and we had a series representation of the hypergeometric function over it. So what I want to do is take the same limit that we got to go from hypergeometric to confident hypergeometric. Let's make two of the singular points confident and push them out to infinity. By this double scaling limit that we were taking, we're going to use that now to generate a series representation. Confident. So the series expansion yeah. As follows. We know that 1f1 alpha z is the limit. I didn't phrase it this way the last time, but think about it. Double scaling limit is exactly this. So derived by rescaling beta and z, push this z up to the effective z up to infinity, and effectively 1 over beta up to infinity. So that's the same as taking the following limit alpha, beta, gamma, z over beta, and then taking beta to 0. Sorry, 0 to infinity. Which if I plug into series expansion, tells me that the series expansion for 1f1 is sum from K equal 0 to infinity, gamma of K over gamma K plus 1 times gamma plus K, so K plus 1, all times Z. Thus, a series expansion for the constant hypergeometric function. So we're going to use this system. But just note that in the same way that we said for the hypergeometric function, there are two linearly independent solutions to its defined first equation. By taking this beta to infinity limit, we can get a second solution in the same way that we got one for the hypergeometric function that had z to the some power 1 to 1 hypergeometric function. A similar thing holds, and write down a general solution for the complement function. All right. So now I want to spend the rest of this lecture working through a particular example of that. So we're going to be working in, again, I want to forget about all the bells and whistles that come with this, with solving a physics problem. Just think about the associated mathematics. So we want to solve units of h bar equal to m1. The time independent surrogate given by minus a half Gaussian acting on some function psi of x. I'm going to go to 3D, so x is a three-dimensional vector, plus some potential. In fact, this is what's going to make this problem special. This potential is a central potential. It's only radially dependent times psi x equal to the energy times psi. So we want to solve this eigenvalue problem. I'm thinking of the Gaussian as an operator. This potential here for the hydrogen atom is equal to minus capital Z E squared over R. Where here Z is the atomic number. And E is the electric charge. Okay. So I'm going to incorporate all of these things into constants that I'm just going to use to subsume all of these things because I don't really care about what these constants are. You can always reinsert them by dimensional analysis at the end. The key feature here is this 1 over R type of potential. The minus sign here tells me that I've got the nucleus of the hydrogen atom, and I define the zero of the energy, the potential energy to be infinitely far away, and the electron finds itself in a potential well, it's the minus sign. Right, so what we're going to find is a series of quantized energy levels, which solving this eigenvalue problem is going to tell us what they are. We're going to find a series of quantized energy levels that get closer and closer spaced, As you go infinitely far away, that goes to 0. So that makes the negative sign. The electron lives in a potential level. Yeah.
Can you say right here that energy levels are going to be closer and closer to station?
No, but we're going to find it later. So reorganizing this equation allows us to put it into the following form. The Laplacian acting on psi of x plus some effective potential, which is 2e plus 2z e squared over r and psi of x. This guy here is going to define for us some effective potential. So this is of the form del squared psi equal plus b effective, which is only a function of r, minus psi equals 0. So this whole problem is radially symmetric. So a priori, I expect that the wave function is also going to be radially symmetric. Right? But let's proceed. Before making any jumping to any conclusions, and I'll show you how the angular dependence is coded. So it's really coded in this operator del squared. But the point is that because I've got some symmetry to this problem, spherical symmetry to the problem, it works best if I convert from Cartesian coordinates to polar coordinates or theta phi. Okay. So in polar coordinates, spherical coordinates, the Laplacian operator looks like 1 over minus 1 over r squared L squared plus 1 over r d by dr on r d by r, or acting on whatever it is acting on, plus 1 over r d by dr. Where this L squared is the angular momentum operator. L squared is equal to minus 1 over sine theta d by d theta sine theta d theta minus 1 over sine squared d2 by phi squared. Okay. So let's solve this problem using separation of variables. So we'll take as an ansatz for psi of r theta phi, separable ansatz where I'm going to separate things in the radial direction and things in the spherical directions, sorry, the polar directions, like this. If I substitute this into this equation here, I'll find that my differential equation, Schrödinger equation, becomes following: minus 1 over y squared times, sorry, minus 1 over y times L squared acting on y plus r over capital R d by dr of r capital R capital R plus R over R. R plus R squared times this effective potential. Yeah. All of this is equal to 0. As you well know from this method of separation of variables, each of these terms involving only the angular variables and only the radial variables must simultaneously equal to a constant. Right? And those constants must cancel out. So we can call this guy minus alpha, and then we call this guy plus alpha, and the two sum to 0. Alpha is a constant. So, well, usual observations when working with separation of variables, we set these two equal to a constant, which means that L squared acting on y of beta y must equal to alpha times y of beta and phi, and d2 by dr d2r by dr squared plus 2 over r dr by dr plus effective potential r minus alpha of r squared times r is equal to 0. This first equation, the angular part, is going to give me some dependence on, is going to constrain the dependence on alpha. And that's all it's going to do for us, because the problem is really is square symmetric. So this is going to tell me that alpha must take values L plus 1 to solve this eigenvalue problem. Physically, this corresponds to the angular momentum. This would be a quantization. What we're going to, all that's going to tell us is to follow the convention and write alpha as L times. Again, L is going to be some parameter that I just mentioned. And I'm going to plug that into. Because the problem is really symmetric, I need to only focus on this radial equation. So to solve the radial equation, I'm going to make a couple of changes of variables. That's going to put it into a form that hopefully I'm going to recognize. As it stands, it's a second order linear differential equation. Doesn't sound like it's too difficult. However, there's all of these R dependencies floating around coefficients that make it not true. So let's change variables. From R to wave function U of R, and U of R is going to be just R times R. In which case, my differential equation becomes a second order equation for U. Looks like this. It's U by dr squared plus 2e plus 2z e squared over r minus L times L plus 1, that's the alpha, that's divided by R squared, multiplied by U. So what this change of variables does for us is it eliminates this first derivative term. So the differential equation for U is the second order differential equation that doesn't have any first derivative. So to proceed, what I do is the following. I rescale my independent variable. From R to a new variable Z, which is defined as follows. Z is going to be R over K, some parameter K, which are some constant K, which I'm going to fix this now. Again, this here is a constant. To be fixed. Next stage. In fact, let me fix it down. I'm going to choose this constant as K squared equal to minus 1 over 8 times the energy. And I want to define, in addition, a new variable sorry, because I made stupid variable choices. Okay. Okay, let's do this. So I'm going to define variable A to be I times Z squared, capital Z here, over the square root of 2e. And instead of dragging this guy around, L times L plus 1, let's just call it B. Should also go back. Change all the variables. Sense. I don't know why it is. All right. So if I do that, if I write it like that, then the differential equation becomes the following: d2 u by dr squared plus minus the quarter plus a over z. Sorry, this is change variables now. If I take this z plus a over z minus b over z squared times u. So, okay, so my claim is that this is in the don't have to do that. I'll show you why. To see that this is a confluent geometric equation. I'm going to write Q of Z in the following answers. Z to the, say, mu, e to the minus mu z. So I'm picking a particular form for this wave function u, and this will transform by differential equation from 1 in u to 1 in f. So the differential equation in f so I should say that the mu and u are again constants to be fixed. They'll be fixed in such a way as to make the form of something like a geometric function equation purposes. So in this case, my differential equation for f reads f z squared plus 2 mu over z minus 2 mu df by dz plus 1/4 minus 1/4 plus mu times mu minus 1 over z squared minus 2 mu over z plus a over z minus e over z squared plus mu squared f equals 0. So now I get to choose what my mu must be. Now choose mu to be the square root. We choose the square to be plus 1/4. And I'm going to choose this guy here to be plus e. So e was, remember, fixed. So e was L times L plus 1. I'm going to choose mu times mu minus 1 equal to L times L plus 1. And that will cancel out these two terms. So these terms are cancelled. This mu squared here will take out this factor of quarter and substituting that again. My differential equation then reads f z squared plus 2 mu over z plus 1 times df by dz minus mu minus a over z 0. This is already in the form of confluent hypergeometric function form. Sorry. Confluent hypergeometric equation. Solve it. To solve it, we need to specify boundary conditions. So I'm going to give you two boundary conditions, one out at infinity, more or less, and one at r equals 0. And these are going to tell us which of the solutions of this second order differential equation we have to pick, but it's also going to tell us something about the allowed values of the entity. The same way that when we solve the Cauchy-Taylor potential requiring finiteness of the wave function fixed for us the energy dependence. Do so here as well. So let's talk a little bit about boundary data. The first one is I'm going to require that my wave function be normalizable. By this I mean that the integral of mod sine squared dtx must be finite. Integrated over all the dimensional space. By plugging in for the variables that we've chosen, you can see that what this means is that u of z must go to 0 as z goes to infinity. And this is consistent with the choice that we made for u equal to a half, because this gives us this exponential envelope, which will take care of these other functions. Yeah.
Just regarding that, we get using the positive group for new cell equals one.
I am choosing the positive root, yes.
So why don't they just find mu as
I could just set these. I just wanted to say that because u squared, I'm choosing u squared to cancel here. I'm choosing u squared to cancel out the quarter. But you're right. I have to choose. I get to choose either the positive or negative root, and I choose the positive root to make sure that u of z satisfies the boundary condition. But let's go to that. All right. Second thing that I require is that the wave function remain finite at r equals 0. Probably z equals 0. So this in turn implies that u not be finite, and this is what sets u to nullness. So substituting these constraints into the differential equation and multiplying through by z, I will find that z f double prime, where the prime is given z, plus 2 times L plus 1 minus Z times prime plus L plus 1 minus A times F equals 0. From here, we can read off what the solution must be in terms of U. You know what the solution is in terms of S, multiply 2 there, and find that U of Z some constant times Z to the L plus 1 e to the minus Z over 2 times 1F1 of L plus 1 minus A 2 into L plus 1 of Z. We're not quite there yet. Because for general parameters, of which there's still L floating around, this combination of the exponential and the constant parametric function will be infinite. And the way to kill that infinity is to require that the power series for the so again, truncates at some point. And the power series will terminate power series for 1F1 terminates when this factor here, L plus 1 minus A, is a negative natural number. Negative integer. So let's call this thing minus n, where n is some positive. So it's this condition that L plus 1 minus A, given that A here contains energy, being some negative integer that defines a quantization condition on the hydrogen atom and all hydrogen-like atoms. Right. So this follows that it then follows that energy of this system must take quantized values as Z squared, atomic number squared. I'm just reinserting various factors now. M e to the 4 over 2 h bar squared times n squared, where little n is calling capital N plus L. Yeah.
I think there should be A squared there, because A is that I. You also have A power 4. Not A
Oh
squared.
yeah, probably is.
Not here, the L plus 1 minus A square. That way there is fine and we get E bar to rest of the job.
That came from. Yeah.
Down there, is that exponential?
Yeah, sorry. In fact, I can take care of the ambiguity in the charging exponential by doing what is conventional and writing things in terms of Bohr radius. I'll do. And then follows then our final solution, psi, labeled by n and L, R. This is equal to constant R to the L, E to the minus the atomic number times Z, that's our times R, divided by A sub B. This is the Bohr radius times N. This is the Bohr radius. Find the H plus squared over N squared. Times 1f1 of minus n plus L plus 1 to L plus 2 to Z and 12 times. That's sufficient for the wave function. Right. Right. 2 more minutes. I would like to use that time to very quickly give you an integral representation for the optical hyperdetermination. And it comes really from Ken. The fact that 1f1 is given as the limit as it goes to infinity of 2f1 alpha. The problem is that 2f1 of alpha beta gamma delta, alpha beta gamma, are very enlightening. I write down a series representation. However, I do know that the hypergeometric function has an interesting property that I think is alpha beta gamma Z over beta. And that is the fact that it's symmetric in its first 2 arguments. So this is the same as by exchange alpha and beta. It's also equal to limit as beta goes to infinity of 2f1 of beta alpha gamma Z over beta. See why I want to do this now. So if I put this integral representation, of the hypergeometric function in here, I get limit of gamma over gamma of alpha, gamma of gamma of integral from 0 to 1 of 1 minus t z over beta to minus beta t to the alpha minus 1 times 1 minus t gamma minus alpha minus or integrated with respect to t. Then you notice that all the beta dependents sitting in this factor here, and the limit as beta goes to infinity of this thing is nothing but the exponential e to the tz. So this then gives us an integral representation for 1f1 as gamma over gamma alpha minus alpha times the integral from 0 to 1 e to the tz t to the alpha minus 1 minus t gamma minus alpha minus 1, provided as usual that the real part of gamma is bigger than the real part of alpha is bigger than 0 for the integral. Okay, so that is all I want to say about integral representations. Next time we're going to be talking about Green's functions and some advanced properties of Green's functions. So the remaining 6 lectures, I guess, altogether. Cool. Thank you.